Hi everyone. I hope you can hear me and you can see me. Uh, Welcome to this session by Rick. So give me a quick thumbs up if I am audible. We'll just wait for a couple of minutes for people to join in, and then I think we can get started. Cool. Thank you for the thumbs up. It's 8:31. So let's wait for a minute or two more, and then I guess we can get started. Um, all right, then let's get started. Once again, welcome all. On behalf of Deep Engineering at Pack Publishing, I would like to welcome you all to today's webinar, Build a Second Brain for Your AI Coding Agents. Before we dive in, a quick word about who's behind today's session. This webinar, this workshop is a part of Packed Events and our Deep Engineering event series. Our goal is to bring experienced engineers, developers, and technology leaders together with industry experts to explore practical engineering topics through technical, practical, and hands-on sessions. I'll share the relevant links in the chat shortly. So the platform that we are currently on is Amit. So let's get the most out of Amit. So before we begin, here's a quick overview of the platform. On the right hand side of your screen, you will find the chat icon. Feel free to introduce yourself, share your thoughts, and engage with other attendees throughout the session. Next, as you can see, below the chat icon is the Q&A icon. You can use this tab for any questions you would like Rick to answer. You can also upload questions from others so we can prioritize them during the Q&A. The next tab that you can see, the next icon that you can see there is the polls icon. If you launch any polls during the session, you'll be able to respond here. And lastly, we have the resources icon where we shall share all the useful links and additional resources here during and after the webinar. So you'll also have the deck of this presentation as a part of this resources icon there. So keep an eye on this section. With that out of the way, it's my pleasure to introduce you to today's speaker, Rick Hightower. So Rick is a Claude certified architect, AI systems practitioner, and builder of production multi-agent system. He has led machine learning and AI development within a Fortune 100 financial services company and has spent years building Gen AI systems, agents, developer tools, and agentic workflows. And if you follow Rick's work, you'll know that he spends a lot of time thinking about a question that is becoming increasingly important for developers. How do we move from simply using powerful AI models to engineering systems around them that are actually useful, reliable, and repeatable? So that makes today's topic very interesting. Today Rick would be sharing more insights on the session that we are having. So yeah, over to you, Rick.
All right, great, thanks. Hey, I really appreciate Denim and Monzi for setting this up and doing all the legwork and yeah, it's been a pleasure working with you guys. So thank you for all of your help and guidance. So this particular talk is one that I'm very excited about. It's something it's kind of evolved over time. and let's get into it. So this is build a second brain for your AI coding agents. It's really how to enable when you're doing loop engineering or graph engineering, how to enable, learning new things, new requirements, new features, discoveries, and how to put that back into the knowledge that lasts longer than a single session. So before I get started, just want to call this out. We do have a follow-on talk on August 29th. We're going to go in a lot more detail on building reliable agentic AI systems. So it's going to cover harness engineering, loop engineering, graph engineering, adversarial agents, judges, and getting sort of the most out of your coding agents and agents in general. Not only your coding agents, but agents that you develop for particular use cases. So this is a common problem, and that I've run into, and I'm sure a lot of you have. If you're using, Claude Code or Open Code or whatever harness you happen to use, you solve a problem, and maybe you spend hours doing this, right? So there's a hard problem, you figure out the trade-offs, and then later on, that session ends, maybe it's running in its own work tree, it's its own feature branch that gets committed, saved, but that knowledge, that institutional knowledge, was never really captured. And then 2 or 3 days later, you start another similar task or one that's related, and you have to go through the whole process again. So the trade-offs are there. Now there's ways to mitigate that, and we'll talk about the different ways. And then we'll kind of talk about the procedural knowledge versus institutional knowledge and what we're sort of aiming at. So before I get started, so the session ended and the answer vanishes. That's the problem, right? So you want memory that lasts longer than a session. And then what things do you want stored in that memory? And what's important for the coding agent or whatever agent that you're dealing with. So there's 2 projects that I'm just going to briefly mention, and then we'll go into kind of the foundation of them. One was this one that I created. It's called WikiTicket SDD, and it's essentially, there was papers about harness engineering from Anthropic, and they were talking about having like a to-do.jsonl file where they would store all the tasks, and they would have the agent sort of iterate and loop until those tasks were done. You can imagine those tasks have hierarchies, so one might depend on another, and one could be broken up into subtasks, and then the subtask might depend on another task, and so on and so forth. So when I was using GST superpowers and sometimes, and also Claude code plans, these all sort of create sorry, I lost the screen there. Okay, I'm back. And these all sort of create their own hierarchical tasks, right? So I wanted a way to take the tasks that were there and share them with stakeholders. So instead of pulling, the original tools that I created, pulled this thing called Agent Brain, and it would pull stuff from Confluence and some other and Jira and whatnot, and try to create indexes over those. And then with this, I want to sort of do an inversion of control and have the LLM drive things. We'll talk a little bit more about that. So making those tickets readily available to the LLM is sort of the goal. And then back to so if that were one of the goals, so I want to make the work that I'm working on, multiple agents, multiple developers, but I want to make it visible. So there's the visible work in progress, so we can involve the stakeholders, the architectural review boards, integrating with other projects, so that the information is there, it's available for human consumption. And Then later on, what we want to do,
Rick, sorry to interrupt. I think if you are sharing your screen, we aren't able to see it. Can you share your
we're
screen?
not able to see the screen.
Yep.
Oh my goodness, that's embarrassing. Okay, let me try. I thought I shared it earlier. Sorry. All right, here we go. Here's the screen. So thank you. So you have the WikiTicket SDD, and it's sort of storing the tasks and the hierarchy of those tasks so that the LLM can easily process it, even spanning multiple sessions. Talk a little bit more about that later. But then later, we wanted to not only make this stuff available to Confluence and Jira where stakeholders can see it, the wireframes, the specs, the architectural decisions, but we also want to be able to store that in such a way that the LLM and the coding agents can readily use it as well. And that's where we come up with these plugins called OKF and PKC. OKF, there's an OKF plugin. We'll talk more about that later, but it's an open standard for second brains or LLM wikis. And then there's PKC, which is basically a describing the SLDC process so that we can consume it within the agents. So let's move on. So we have 3 failure modes. Going back to the original, hey, this decision, this thing that we're working on, it didn't last longer than the session. So the more stuff we kind of throw at the coding agent, the more management we have to do. We may have to put things in Claude.md or agents.md or create agentic skills, right? So that it can remember these things. And we'll talk more about those memory layers later. But that's sort of the idea behind it. The more things that we're doing, the more things that we're throwing at it, it seems the more likely that things will get lost. And that's what we're going to try to mitigate. So we don't want to relitigate decisions. We don't want to, let's say we do a discovery or a spike and we figured out which trade-offs that we're going to go with. We don't want to, forget that knowledge when we're, iterating and adding new features or working on similar features. And we don't want the knowledge to be tribal either, right? So if somebody tells me something and then I put that in the current coding session, but that never gets stored anywhere, or it gets stored maybe in Confluence, but it's not readily available to the coding agent. That's what we're trying to avoid. And that could be chat logs, things you overhear, meetings, sort of one-off comments, Slack, Teams, whatever. So how do we ingest and keep that information? So that's what we're talking about today. The repo is the second brain. So we're going to set up a repo. One is we're going to do the visible work so stakeholders can see what we're doing. And then 2, be able to write that same work, the same knowledge graph in such a way that the agents can pick it up, right? And even within different branches, different work trees, they can access the same data. And then we're going to talk about some projects that used these techniques. And then this is all kind of leading up to the bigger talk on August 29th. We'll go into a lot more detail on loop engineering, setting goals, harness engineering, graph engineering, where some of this fits. So this is sort of a lighter intro to deeper subjects, but with a small spin. So we have these different layers. This is sort of the memes, the viral things that pop up, right? Where there was prompt engineering, and then you sort of mastered that, and then context engineering came out, and you're like, well, a lot of what I was doing in prompt engineering is actually context engineering. And then there's harness engineering, which is sort of the right pieces at the right time, and controls in place so that the LLM can interact with the computer. So you have these agentic computer interfaces and tool calling and tools that can be deterministically blocked under certain conditions. And then you have loop engineering, which is sort of setting goals and repeating the process until a goal is met. And then with graph engineering, we're getting into, orchestrators and judges and rubrics and providing feedback and setting loops and exit loop conditions. But this sort of whole graph of decision, breaking tasks up into smaller pieces and then putting them all through the different sort of judges and loops and whatnot to improve the output. So we're going to cover all that in the longer talk on the 29th, but it's sort of germane to this as well. So this is going in a little more detail on that last slide. So for context engineering, if you're using a coding agent, you're going to want to put things in Claude.md and agents.md, like, hey, these are the frameworks they're using. This is our coding style. These are sort of the rules to use this code base. And that's also where agentic skills come in. So that is, and then the harness engineering is basically when those get loaded and how, right? So if you're working on a certain use case, let's say you're hitting, doing a CDK deploy, the harness is going to see that you're doing a CDK deploy. It's going to say they probably want to use this CDK skill to deploy the AWS. So it's what provides the loading of these context systems at the right time. And what we're really trying to do with both of these is avoid overloading the LLM with either stuff that doesn't matter for the task at hand, and we're trying to avoid things like context rot, context panic, and the U-shaped attention curve, where the important things that we want done are just basically getting ignored. So we're trying to avoid those things, and that's sort of what harness engineering is. It's this mechanical sympathy, but instead of mechanical sympathy for like a computer server, a modern computer server, it's mechanical sympathy for how the LLM can interact with your computer system. Let's move on. So the harness is the control plane. And then there's constraints. And we talked about these. With the context, there's constraints. Not everything's going to fit, no matter how big the context window is. Typically, not everything will fit inside of it, at least not yet, right? And even if it did, you don't really want everything inside of it. You want the things that are needed for the task at hand, right? So we know that we have this problem of strong recall at the beginning and end. So we do things like have scratch pads and we keep the most salient information either at the beginning or the end of the prompt. We have this lost in the middle issue. We have token cost. There's just having the wrong context. You could be working on a task. Maybe you're doing a bug fix. You don't clear the context. Now you're working on a new feature, and it's kind of getting confused with the two conversations, right? So it's not just having the right amount, but it's the right content in your context as well for the task at hand. And that's a lot of times what we're trying to do. So teams have done stuff, and there's tools available. For example, Claude Code has auto memory. So if something's very salient, it will remember that. And you can even say, hey, remember this. It will remember that. So if you run into a problem, you can say, remember this, and it will remember how you fix that or what that discovery was. But the problem is that's just on your machine, right? It doesn't get checked in to version control. In order for it to be shared, you're going to either have to put it in one of the rule files, right, which are get kind of boxed up, or you're going to have to put it in your Claude.md or your agents.md. So that's a skill that people have to have when they're working with these systems. Whenever there's something that they need to get repeated, they should probably go through those files and not only add things to them, but also go through as the project changes. We refactored and we wrote this subsystem in Rust now. It's no longer in TypeScript. Well, you probably want to take out those TypeScript rules, right? So it has to be kept up to date, and that is a manual process. And that's another thing I want to cover. Whenever there's a manual process, there's a good chance that you're going to forget, right? So we need some way to have a process that can be managed by the LLM itself. So You can also use a local vector store on documentation. Maybe you pull down a bunch of Confluence docs and a bunch of Jira tasks that are related, and even code bases. I've done that with Agent Brain. The issue there is it loads these items, but it doesn't necessarily know what the relationship is. So it might pull a document that's an older decision that you've moved away from, or something that applies to another project. So it doesn't have the context to know exactly where that fits. And there's techniques to get around that, but that is an issue, right? So let's talk about how to get beyond some of these issues. We talked about the harness as the control plane. It's going to be the one that blocks certain tool calls. It filters data from tools, right? So that you don't, if there's columns that you don't need, or if you want to do pagination, it would handle that so that you're not flooding the context memory and then causing downstream issues. And it does that precision context injection. It's going to know when to read a particular claude.md file, or when to read a rules file, etc. When to load an agentic skill, what tools to use based off of their descriptions. So the harness is this control plane that kind of decides, what gets loaded into the system when you need it. But there is 3 forms of memory, and that's kind of what the harness is managing. It's managing this working memory, which can consist of, at different times, agents or claude.md files that get loaded, skill files that get loaded to perform a certain task, or certain MCP tools become available depending on what you're doing, etc. So we've got that pretty much covered with the agentic harness and agents and agentic skills, right? But what we're missing is this larger institutional memory. So this is the how, that's the procedural memory, that's agents and agentic skills that you can write, very important to do that. This is what's happening now to perform your task at hand. But this is all the reasoning behind all of these things, and the way things are laid out, and the task, and the epics, and the stories, and the architectural decisions, and the results from discoveries and spikes. So this is the larger layer that we want to get access to for the projects. And these are the improvement cycles. Maybe we have multiple agents trying different approaches to something. This is where the results of those improvements get stored. So let's go into a little bit of that. So again, our procedural memory is just agents, CloudMD, agentic skills. Our working memory is what's actually loaded inside of the coding agent at the time of execution to perform a task. And then what we're after is this larger institutional memory. And a lot of times this institutional memory, it might exist in an email, in some meeting notes, in a Confluence page, and it's sort of scattered about. And the one thing we know about wikis that are managed by humans is they don't always keep things up to date, right? The design docs are, from 2 years ago. The architectural decisions are maybe not the latest ones that had the workarounds once the rubber hit the road and we actually had to go to production. So all of those things sort of get lost in the stream of time, and you have sort of a stale snapshot of what the system was at a certain point in time, and it's harder to kind of keep those in sync. But that's where an LLM really comes in nice, because it's really good at keeping an LLM wiki at sync. So we'll talk more about that later. So yeah, this kind of says the same thing. So what's nice about this format, and this is the OKF format. It's if you're familiar with the way agentic skills work, they have this thing called a partial disclosure architecture. So you have a skills.md file, and it will refer to scripts and references. You have a references folder. Typically those references, each one of those files are quite small. They'll have a table of contents at the beginning, that describes, what each section is, so that the agent can do a grep command and jump right to the section it needs. So it's laid out in such a way that you don't have to load everything. So if you had like a modern Python agentic skill, it's not going to throw the whole modern Python book into your context, because you wouldn't want that. But if, let's say, the coding agent needed information about how to use thread pools, it could navigate that skills MD, which would push it to a reference file, which would tell it what location in that file to look at. And it could load, sort of what it needed at that time. So it's not going to load everything. It's not going to overwhelm, but it's going to partially disclose the pieces it needs. OKF has the same mentality with the partial disclosure architecture. The difference is it's dynamically being created over time. You're storing, different pieces of knowledge that then the LLM or the coding agent can pick up fairly efficiently, as probably efficient as it would if it were an agentic skill. But agentic skill is sort of frozen in time, right? It's this version of this skill, and it has to be edited and released, where the agent brain, if you will, the second brain rather, can evolve as you go through use cases. Okay. So we're going to build it on top of OKF. And when we do that, we want to have, so we have the brain that provides judgment. That's the agent itself. And we're going to feed it meeting transcripts, Slack threads, maybe a PR description, a PRD, whatever, into the system. And then it's going to use these plugins to write that in a format where it can be read easily. Where with an agentic skill, you're laying things out once, maybe you optimize it, but then it kind of stays that way. With this, you're constantly adding it. So you have this extra layer that knows how to do consistency checks, traceability, make things sure they're complete, make sure there's not too many hops, right? So that they can be loaded efficiently, and do schema validation and such. That's right, schema validation, because each plugin is going to have a different set of nouns. So let's briefly review. So why would you want to store things in a repository? This isn't necessarily the same repository as the project. This would be another repository that maybe multiple projects share, or a whole set of microservices, or a set of related pieces to a larger system. It's already reviewable. Humans can read it. They're just markdown files. It's attributable. You can figure out where it came from, who created it. It's mergeable. So I could be working on one work tree, doing some investigation. When I'm done, I create a PR. It makes the change to the main work tree, and then everyone that uses that, the next time they pull main, they're going to see that information. And what does it buy you? Well, if you have a new teammate that joins, they can come up to speed really quickly. They could even go in and start asking it questions about the applications and how they relate, why this was decided, why we're using this versus that, and all that data could potentially be in that second brain, which is not only usable by agents, but is also usable by developers. And then the day they get started, they're not making, relitigating things that have already been decided, because they have access to, sort of the why and the how. And more importantly, so do the agents. So what are the problems if it's only under Git? Well, most of your stakeholders are probably not going to dig through your second brain, right? They're probably not. And they may not be developers, but they may already have their own tools like Figma or Confluence or Jira, right? So what you really want to do is keep those things in sync, but they're not really the statement of truth. The statement of truth is your what's in your Git repos, right? And then everything else gets sort of updated. That's not to say that they can't write specs and PRDs that later get ingested. It's just that what's in your second brain is sort of what's in the institutional knowledge for the agents. But you definitely want to have, if you have an architectural review board, you want to be able to update documents that they can see. You want to update roadmaps so your product manager can see them, design documents, code walkthroughs, all that, so developers that are joining the project can understand. So there's a human view of the systems, and then there's the internal view. And that's where the WikiTicket SDD comes into play. So that's WikiTicket is basically you either go into planning mode or you use some sort of spec-driven development, and it's going to convert those into that to-do JSON-L file. And then from that to-do.jsonl file, it's going to output different documents like release notes, requirements, design documents, PR descriptions, etc. Those all sort of become automatically generated based off of the tickets and the other pieces. So there's hooks that turn plans into tickets. So typically, if you're doing like Claude Code or Grok Build or Open Code, when you do planning, it generates a list of hierarchical tasks. They're task lists, tasks relate to other tasks. It converts those into this JSON-L file that then can be transformed into these various documents with different plugins and whatnot. So you have epics, stories, phases, plans, release notes, requirements, etc. And they're up to date because it's the Git repos are the statement of truth. Now, that's great to get to share with the outside world, right? Which is important. People are important. Stakeholders are important. Spent a lot of time on, how do you organize things in something like Confluence so that a person can go in and find the stuff that they need. I did spend some time on that, some information architecture. But the WikiTicket system is just sort of the current view of the system. Different branches, as they get merged, will update that view, right? And because you have agents that are working in work trees and branches, and potentially many, and many developers as well, you want a way to collaborate that where you're not clobbering over each other, right? And that's what WikiTicket provides. Well, first it can transform the tickets into epics and stories and tasks and all those other things that we talked about. And it provides that visible work in progress to the stakeholders, the humans, the product managers and architecture review boards and whatnot. But then also we can have multiple agents working on the same data, and we need a way to make sure that, what agent A does doesn't clobber agent B. And that's where this all comes down to an event log. So things get written to the file. And then when they get merged into main or whatever branch you decide, it consolidates those changes that happen in potentially multiple repositories into one set of tasks. So there's a log, merge, and then from that merge, you can create different states, and artifacts, which are over here: a roadmap, design document, ADR, decisions, assumptions, etc. So that's kind of the idea of keeping that in sync. But then we want a way to retrieve, not only the humans retrieve, but we want a way for the coding agents to retrieve, right? And that's where we start using OKF to write these LM wikis. And then once we do that, then things start surviving single sessions, and they start to surviving even, planning sessions, and people using different spec-driven development or different tools. Like one person might use Claude Code plans, one person might use superpowers, one person might use GSD, all in the same project. But as long as those get written eventually to the JSON-L files, they can be consolidated. So it lasts beyond just a single session, a single developer. and it becomes institutional memory. So in order for it to become institutional memory, we need a way to write that out. We're using the OKF standard underneath. This is a little bit about the OKF standard. We won't go into a lot of details on the low level bits of that, but it's important. I think it's an important technology that you should master. But what we're going to do is we're going to have a way to capture that, the stuff from the wiki, and sorry, from the spectrum of development, the wikis, the plans, those tickets, that JSON-L file, and capture that and store that information into the second brain. And what we have for that is PKC. And you can think of PKC as where WikiTicket is writing to Confluence and or human wikis and document systems. It integrates with, for example, Azure DevOps and whatnot. So it's writing those things where people can see them, it writes reports and whatnot that are consumable by people, release notes. The PKC is writing the same information from that JSON-L file to a knowledge base. So it's all the SLDC information that you need: epics, tickets, tasks, subtasks, bug reports, etc. Discoveries, spikes, architectural decisions, and it's writing that to the second brain where it can then be used later by these coding agents. Now let's think about a typical use case. So here, let's say, hey, I had a meeting with the architectural review board. We were going to do things one way, and they said, no, we want you to use, we don't want you to use the IAM. We want you to use an authentication so that people can authenticate with GWT, and we don't want to use cookies, or maybe we do, we're not sure yet. And so you might do a spike where you try multiple implementations using multiple providers. You have the architectural review meeting where there's an initial design and an initial set of sort of mandates, requirements. There's a decision to use JWT, maybe that's from the ARB, the Architectural Review Board. And then there was things that you assume because you're a developer, maybe everything's not spelled out, but you're going to make some assumptions. And then you're also implementing this feature. And this, as you're implementing this feature, it may need to refer to those why you picked, this, what was the reasoning, right? So it doesn't make the same mistakes. It may need to know what the decision is, what the sort of the origins of that decision is. If it's just an assumption, right? Let's say that starts to run into a bug. Is this something I can change, or was this in the ARB, right? So it starts to have a provenance of where these items came from. It becomes very important for the decision making. You could think of the OKF as writing down the relationships and reasoning between these nodes, and then the coding agent or agent being a reasoning engine, right, that uses reasoning to kind of figure this out. So it's laid out in a way where it can use its reasoning abilities. So, I mean, what are your alternatives? You could just, have a bunch of markdown files and, kind of scan them and dump them, or maybe read all the files from your Confluence and create some kind of mechanism, maybe a vector similarity search, but then this doesn't have the causality, right? So when you organize them in a second brain or in an LLM wiki with OKF, you have these relationships. So this root agent node depends on node A, and it includes node C, but it affects node D. And you can sort of define these relationships and what's stored in these nodes. And that's what those various plugins do. So I have plugins for translating, what comes out of WikiTicket. I've got plugins that, reverse engineer system architecture, or either by design or by code, or by looking at you know, Terraform files or whatnot, and putting that in such a way that it's indexable and readable, or, you know, data engineering concepts. So let's just move on back down because I know it's coming up. So what you want to hand the agent is this sort of pack of causality, decisions, assumptions, nouns that are pertinent to what it's doing. A noun would be like a ticket, an epic, a decision, a discovery, etc. And then provenance. So when you're laying out the LLM wiki, there's rules that you want to follow, just like when you lay out agentic skills, so that you can read those back more efficiently. This is what this slide is talking about. And that's kind of baked into these various plugins. So again, you had this one plugin, PKC, that's the why, meetings, decisions, experiments, assumptions, questions, requirements, features. It's the SDLC reasoning graph, right? And then you have the SAC, which is the sort of what's there, how is it deployed, you know, what's the topology. And then there's something similar to that, but this is for, you know, lakehouse, data lakes, catalogs, tables, lineage, medallion layers, schemas, semantic layers, etc. So things that you would need for that. So again, PKC is basically the adapter from the WikiTicket SDD to the knowledge graph, which is the second brain, the Wiki LLM, and then you have different flavors. I've actually added, like, now there's not just these two, there's like 15 or 20 of these for different nouns. They all have different nouns, if you will. I think we talk about that somewhere. I guess it was on the other slide. So they all have different nouns because they're looking at different aspects of the project. Let's go to this. So, you know, a simple graph is just a loop where you're just trying to improve something. But we know that, you know, these are usually multiple agents in different roles that do split up work and have different graders and implementers and researchers and verifiers and judges, and there's rubrics and whatnot, right? But let's say that we have this verifier, and the verifier is, let's say it's verifying pages out of a report that we're generating, or maybe it's verifying that the UI has the right layout. So where is it going to get the data for the verification? Well, if it were talking to the knowledge base or the Wiki LLM or the second brain, it could look up the wireframes and the requirements. And then when the loop finished that screen, we could have a second agent that knows about the wireframe and the requirements and maybe the mockups, and knows that it needs to use those to judge the implementation, right? So that knowledge becomes important. And maybe there's something in the wireframe that just doesn't exist in the data set, right? So then there would have to be a decision to say, well, you know we wanted that, but we don't have any way to get it out of the lakehouse yet because that's not getting landed. So let's add a ticket to look into that. But for now, we'll take it out. And that sort of decision has to be made and stored somewhere. So, you know, we would store that potentially in the knowledge base as part of this loop. So you could think of this as you're doing discovery and you're improving the output over time. So here is a typical loop. You have the discover, plan, execute, and verify. Well, in the discovery phase, once you discover things, you don't want to keep rediscovering them, right? You need a way to store them. So when you're thinking about graph engineering, you can think about things like orchestrators and judges and doers, and providing feedback through a rubric and separating the context, right? That's one way to look at graph engineering. But if you look at tasks and their hierarchical nature, when you're doing work, right, like you want those agents in the graph to be able to look up the requirements, the wireframes, the reasoning, the schema, the catalog, whatever it needs to implement that feature at that time. And you want to make it in a way where it can load it as it needs instead of loading, the whole encyclopedia of everything, right? So that's the other sort of aspect of graph engineering. And then there's the improvement cycle. Once you've made a decision and you want that sort of to be stored and remembered. So two recent use cases that I worked on within the last month. One was pulling an ontology from a set of PDFs. It's actually several different ontologies, so you can think of different schemas out of the PDF. And so I would have PDFs. I know what's in them, right? Because they were simulated, we wrote them. And I know what I need to extract. So I have some rubric to see, if I've extracted things correctly. And then as we add new features, those change. So here the goal is to hit a certain score for the extraction. Once we add either new document types or new rules or new parts of the ontology, we want to make sure that the other parts didn't break. So this was implemented with a LangChain deep agents, and it takes several inputs, different document types and whatever, and then it can tune an application that can extract data from PDF. And basically what it does is it tunes the prompts that are used by Sonnet 5. And then I did something similar. This time I did it with the agent SDK, but basically the same idea. I have a goal. We're trying different things. We're editing both the code, rubric, back from that, and then we can essentially include that and make sure that we don't have regressions. So these are two systems that kind of generate, I would call them parsers. One's parsing a transcript, looking for certain language fragments, and then giving a score to see if the person on the call, it basically grade how they did versus what they were supposed to do on the call, and also look for negative things, what they're not supposed to do on the call. And then this one was just extracting things from various PDF documents for a certain use case. So both of these are sort of self-tuning loops where they have to try things and store what they tried and improve their grade. And that's where something like this can really help out, as well as just your normal development cycle. It's kind of why I created this system. I was working on a project where there's a lot of legacy systems, there were a lot of requirements coming in. They were coming in through conversations, meetings, Teams discussions, Slack, and I needed to kind of get them all moving in the same place and recorded, as well as, we might have a requirement, but we don't know exactly how to get out of the lakehouse. So there's a lot of discovery. We're just kind of walking the schema, looking at data, looking at columns, and trying to decide how if the data is even in there that we need, and if it's not, how do we get it, and add that as tasks. So you can think of it as a self-improving loop. So here you seed with the content pack, you discover something is wrong or assumption or something is missing, you decide how to move things forward. Maybe there's some additional tasks, and those features will be added later. You write the correction back to the second brain, and then the next pack where you retry this improvement will be there, right? So it's sort of a growing system, knowing what the results were of the work, whether that's a spike or experimentation or discovery, walking the lake house with a set of, hey, we need to figure out how to do X, Y, Z based on conversations and whatnot. And then we got to make a bunch of assumptions. I don't know if you know this, but sometimes you guess and you say, we think it's this, and then you share that with other people, right? And then you implement something that works, maybe. I mean, it works, right? But it's not exactly what they wanted. and then they tell you what they actually wanted, and then you go back and iterate, right? But you got to kind of show people, and there's that iterative process, and that's where this really helps out a lot. So that's the idea behind it. Self-improving loops need a way to store discoveries. They need a way to store, the results of experiments. If we try 4 different approaches, which way works and why? Why didn't we pick the other ones? Because as we come up with similar tasks, it sort of grows and evolves. So I think you could start this pretty simple. You start with a couple of context packs. They're all written as plugins. They're written as Claude plugins, Codex plugins. It's the same kind of code base, just slightly adapted. So it's Claude, Code, and Grok natively. And then it also supports the universal plugin format. But then you lose sometimes some hooks, but you can add them back. But anyway, the point is there's plugins that support all different types of coding agents that will write these nouns and ideas and ontologies to a knowledge base that then can be consumed by the agent, where you can do this experimentation and have it remember what the results were of the experiments. So what we covered today is this sort of mental model, the event log and deterministic folding, how we generate documents for humans, how we generate documentation and knowledge for coding agents, how we keep those separate, how we can have multiple coding agents work on the same project and not step on each other's toes. And then we covered a little bit of loop versus graph engineering. On the 29th, we're going to go into more details on defining rubrics, graders and judges, regression suites, self-improving loops, including human feedback. This was just a taste of what we're going to cover later. And with that, remember, we've got this thing on the 29th. Use code RIC40 for 40% off. Links are in the bio. I don't know what that means, but the links are there. Denim and Monzi will provide them. They were probably pointed there. These repositories are all out there if you want to try this stuff. I'm always experimenting with different things and playing around and trying things out. I have a blog. I'm writing a book on harness engineering and agent memory, and working on that with Chris Mathias. We've got the talk that we're giving the 29th, and then we have the harness engineering blog on Substack, and there's another 2 more blogs we have over there on Medium, which you should be able to find. With that, let's open up the questions.
So thank you, Rick. That was a fantastic session, and I hope everyone found it as insightful as I did. I particularly like that this moves the conversation beyond simply asking which AI coding agent should I use, and towards a much more interesting question: how do I build an engineering system around these agents? Before we move on to the questions, I also wanted to mention something. Would like to go a bit deeper with Rick after today's session. I think that's what Rick mentioned towards the end of his slide. Rick will be back with us on Saturday, 29th of August, for another session called Engineering Reliable Agentic AI Systems. And this is really a natural next step forward from what we have discussed today. Today, we are looking at giving our coding agents better context, knowledge, and memory. On 29th of August, Rick, as he said, that he's going to go a bit deeper into what happens when you want to take agentic AI beyond experimentation and start building systems you can actually rely on. It's a practical hands-on workshop covering areas including system architecture, harness engineering, and loop engineering. You'll get into things like evaluation and testing harnesses, context management, observability, designing agents, human in the loop workflows that can operate reliably without wasting huge amounts of context and tokens. So if today's session gets you thinking, okay, I've improved how my agents work with my knowledge, but how do I actually engineer the system for production? Then the 29th August workshop is designed to answer the next question. And we do have a special discount for everyone joining us today. I think Mansi has already shared the link as well in the chat. So when you register, use the code RIG40, or the link will directly take you to the discount code, and the special discounted rate will be applicable while you purchase the ticket. We'll share the registration link as well with you again in your emails, so that you can continue learning with Link. And with that, let's move on to your questions for Rick. So yeah, I think we have the first question that's there already on the stage. That is by Ryan. Thanks for the talk. Have you found novel ways to reduce token usage? Example, non-embedded semantic layers that organize code by abstract syntax trees. Take that up, Rick.
Is that written down somewhere? Because I didn't quite follow that. Is that, let's see, questions? Q&A, okay.
Yeah, you can say it on the stage as well.
Novel, okay, I see that first. Have you found novel ways to reduce token usage, e.g. non-embedded semantic layers that organize code by abstract syntax trees? I worked on a project called Agent Brain, which had a graph and a vector over a set of documents, it was very efficient, as opposed to, if you have the agent sort of going out to Confluent, searching for things and pulling it down itself and searching through documents. So it was more token efficient. But yeah, I kind of get where you're going with the abstract syntax trees. Absolutely, I played with that. I would also say that one of the things that this project kind of does is it does have the different plugins have different nouns and properties, right? That you could think of them as schemas for different activities. And the way that OKF is laid out is just like an agentic skill, because it's using the PDA, it's really efficient for what it loads from the context. It doesn't load everything. So in a way, yes, it's done by that, but I know there's other techniques and tools that people use as well, and have dabbled with those.
Hope that answers your question, Ryan. Yeah, we have another question by Ryan. How would OKF maintain portability? What general approach would you take for agents to prevent data in Lakehouse from persisting in persisted knowledge?
Well, that's a good point, I suppose, especially if you're dealing with different regulatory requirements. Typically, the things that I'm storing in the knowledge base would not be the data that's in the database per se, but more about the metadata, like the schemas, how things are related, where things are stored, what's in the bronze layer, what's in the gold layer, what's the actual ELT job that's pulling the data in, what's the lineage, what transformations are done, workarounds and caveats and catalogs, not really, PII data or anything per se. And then it's just stored in the markdown format, and it's in a private repo. So, but it's just like, it's like anything else. You wouldn't store a password in an agentic skill, or you wouldn't put a password in your Claude.md file. So it's sort of the same approach here. Is you shouldn't do things like that. Is there anything that prevents you from putting a password in a Claude.md file? No, you could do it, right? Could you actually go and write this? Yeah, you probably could, but I think if you tried to write a password, the coding agent would try to block you. But we should probably add some hooks in there and some rules within the plugins as a kind of a second layer of control, or second line of defense. But yeah, that's a good point.
Cool. I hope that answers your question, Ryan. Again.
Yeah, as far as portability, I want to say something about portability. So since I wrote this talk, and since I don't know about you guys, but I tried this thing called Grokbot, right? And then I had all these local agents doing things on my machine, research, outreach, marketing, whatever, running on my laptop. Most of them, the Claude code based or Claude agent SDK or sometimes a LangFuse, not LangFuse, I always mess that up, LangChain deep agents. So I have these different agents that are running on my machine, and then I have these Grok bots, and they're doing kind of similar stuff. I was like, man, it would be great if they could share data. So I defined, I have all my different Grok agents, marketing, sales, whatever, engineering. And I started creating these repositories and these nouns, these plugins that are specific to these different job roles, stuff that I was already tracking before, but now I have like a language for it, right? So now things that I do on Grokbot is now available to the agents that I'm running locally and vice versa. So I've got that kind of worked out where Grokbot and my local agents can share information. So I thought that was kind of cool. It's not this talk, but it's using the same OKF, but different context packs. There's a context packs for, the CTO, the marketing guy, the publication specialist. I forget what they're called, but and then so now I've got Grokbot communicating back and forth with things that are happening on my local machine, which I think is cool.
Yeah. I think there are no more questions. So that brings us to the end of today's session. A huge thank you to Rick for joining us and sharing not just concepts, but the practical thinking behind building a second brain for AI coding agents. And thank you to everyone who joined us and contributed your questions. Once again, if you'd like to continue learning with Rick, his next hands-on workshop, as we said, engineering reliable agentic AI systems, is happening on 29th of August. Remember to use Rick 40 when registering to get the discounted rate, or you can click the link that Mansi has shared in the chat section, and it'll take you directly to the discounted link of the event. So thank you everyone. Have a great rest of your day, and we hope to see many of you again on 29th of August. Thank you, Rick. Thanks, guys.
Thank you, guys. Thanks, everybody.
Have a great day. Bye-bye.
Bye.